Hello, and welcome to the video accompaniment for Chapter 7, Section 3 of our text. In this video, we'll be talking about the division algorithm. After reading through the section in your book and watching this video, you should be able to apply the division algorithm to some specific examples, compute the div and mod of two integers, so we'll introduce a new operation between integers, div and mod, and you should be able to use the mod operation to prove divisibility results by cases. And so we'll see an example of something like that in this video. All right, let's get started. Now, before I state the division algorithm, I first want to ask a very fundamental question to what we're doing. And that is, what does it mean to divide? So at one point when I was a graduate student, I taught pre-algebra at Western Michigan. And one really important thing I learned from teaching that class was just how much you can learn by revisiting some really fundamental questions. And most of you are probably so far out of that time in your life when you were first asked these kind of questions and defined what it meant to divide, that maybe you've forgotten some of it by now and forgotten some of the tools you use to understand it. So I'd like to remind you of that and then use this to motivate what the division algorithm is. So let's say I want to do something like 11 divided by 3. Well, what is this asking? How do I know what the right answer is? Actually, I'm going to change this. Let's do 11 divided by 4. How do I know what the right answer should be? What does it mean to divide? And so you might, I don't know, just take a calculator and plug it in and show me 2.75. That's what it is. But what does that mean? Well, how do you know? How do you know the calculator's not lying to you? Okay, so anyway, so we use this really nice model in the pre-algebra class of division. And what division is really asking, it's saying, how many groups of 4 can you make out of 11 objects? So we use this model, right? I'll draw 11 objects. I'm just going to use circles here. There's my 11 objects, and that's what's great about math, is that it's general. It applies to everything. It's abstracted beyond the real world. So we just have 11 objects here, and this is asking how many ways can I divide, or how many groups can I make with 4 objects in each one. And so I'll just start doing that. I'll divide it up into groups of 4 objects. And then, so it looks like I have 2 full groups and, some bit that's left over. So how can I express this bit that's left over? Well, I could say it's some fraction of a whole group. So in this case, it's 3 objects out of a total of 4 objects that could be there in that group. And so that's 3/4, and that's how we can write this. So we can say 11 divided by 4. Well, we could write this as 2 3/4. So I use the mixed fraction there to say this. Of course, I don't know about you, but I personally hate mixed fractions. I'd rather just write them as addition, which is what they are, 2 plus 3/4. And so that's a nice way to state what 11 divided by 4 is. And of course, you might have showed me 2.75. What does that mean? So 2, same thing as 2.75. The 0.75 here is the decimal expansion of the fraction 3/4. So that is, we write 3/4 using the decimal expansions that I talked about in the divisibility rules video. So that is 3/4, only this time we use negative powers of 10. So this is 0.75, right? So this is 7/10 and 5/100. And so I could also express it like that, and that's why we write 0.75. Okay, but how else can I answer this question of how many ways can I make, or sorry, I keep saying how many ways. This isn't combinatorics yet. I'm getting ahead of myself. How many groups can you make? How many groups of 4 can you make out of a set of 11 objects? And so the other way I could answer the question of what 11 divided by 4 is I could tell you how many sets of size 4 there were, and then how many were left over. And so what I'm going to do here is all I'm going to do is take my initial thing, 11 divided by 4 equals 2 3/4. I'm going to multiply the whole thing by 4. 11 equals 4 times 2 plus 3. And so look at what this is telling me in this restated form. Look at what I can pick out. I can pick out how many groups of 4 I could make. So in this case, it was 2 groups of 4. And how many were left over? That's the 3. So we call this how many groups there are. That's the quotient. And how many are left over? Oops. That is the remainder. All right, so why am I telling you about this? Well, let's look at a different example. Let's do 12 divided by 4, or 12/4. Okay, well I could draw my 12 objects, split them into groups of 4, and in this case I'll see that 12 divided by 4 is just 3. And so notice I could also write that. I'll say if and only if 12 equals 3 times 4. And so if I can write it like this with a quotient and a remainder, and I see here that my remainder is 0, well, that's telling me something really important about the relationship between 12 and 4, right? It's telling me that if I split it into groups of size 4, that there won't be any left over. And so that's exactly what it means for 4 to divide 12. So 4 divides 12. If and only if, or I'll just say 4 divides 12. Yeah, I can say that. If and only if 0 remainder. And so, right, I don't just want to do 11 divided by 4, 12 divided by 4. I want to be able to do this in general. And so in some way, this is telling me about the relationship between 11 and 4, 12 and 4. The thing that's being divided by the other thing. It's telling me about their relationship. And so if I can come up with efficient ways to calculate the quotient and the remainder, well, then this gives me a nice way to figure out if something is divisible by another thing. All right, let's check it out. All right, so what's the division algorithm? It's just stating that we can do that for every pair of integers m and n. With some caveats. We'll make it a little bit more rigorous than that. Put a couple more restrictions on there. For every 2 integers m and positive integer n, there exists unique integers q and r such that m equals n times q plus r. So writing that division by expressing how many groups of size n there are in m objects. So notice this restriction here that we place on the remainder. So if we put this restriction on there, we say, hey, when you talk about a remainder, it better be between 0 and n, exclusive on the n, inclusive on the 0. Then this will guarantee that this integer q is unique and that the r is unique to this pair m and n, so that there's really only one way to do this, and that's pretty important. Especially when you want to define maybe operations based on this process, which we'll get to in a second. For right now, let me just show you a couple examples of this. So if m is 58, let's do m equals 58, and n equals 9, well, then we can write, it doesn't matter what 2 integers I give you so long as n is positive. I can write 58 is, okay, how many groups of 9? Well, I know what 9 times 6 is 54. So that would be 6 groups of 9 with, and then there'd be 4 left over. So, yep, I could write 58 that way. That's what the division algorithm is telling me, is that I can do that. And notice that there's no other way I can do this, that I can write this, as long as I make sure that that 4 is between 0 and n. So it's kind of telling me how I should express that remainder. So let's look at one more example. Oh, how about an interesting one? Let's think of something interesting, so we don't get bored. What if m is 0? What if I do 0 divided by something else? How does this look? Well, sure, we can do that. 0 equals, how many groups of 7 can you make out of 0 objects? Well, you can't make any groups. 0 groups of 7 with a remainder of 0. And so here the quotient is 0 and the remainder is 0. Notice the remainder is 0, so that means that 7 divides 0. And in fact, we'll be able to do this for any integer, right? 7 wasn't special, so we recover this, this result again that every number divides 0. All right, how about another interesting one? What if m is negative? We know n needs to be positive in order for this to work, but what if m is negative? Let's do n equal 7 again, why not? Well, okay, let's write negative 58. So it gets a little bit weird, but we can abstract beyond the diagram, right? So how many groups of 7 out of negative 58? Well, I know 7 times, we got to think about this one, right? Well, I know that r has to be positive for this to work, right? And so I'll do, so how many groups of 7? Well, I could do negative 9 groups of 7. That would put me to negative 63. So negative 9 groups of 7. That puts me at negative 63. And so that's a remainder of positive 5. And so that works as well. In this case, we have to go down to the next integer. And so in the negative, well, in all cases, we have to go down to the next integer. However, when it's negative, that looks a little bit different, right? We get bigger numbers because they're negative. That's what going down means for negatives. More on that later. What if m is 24 and n is 6? Well, I can write 24 equals what? 4 times 6, 4 groups of 6. And so there again, I'm seeing the remainder of 0, and we know that 6 divides 24 since 0 remainder. Yep. So as I said before, it'd be nice if we had some way to just calculate this quotient and remainder without having to think too hard, without having to draw the diagram, and maybe apply it to negative values for m as well and understand that. And so we can do that, and this is the concepts of div and mod. So these two, at the end of this, we'll introduce these two new operations on integers. All right, so given n and m, division algorithm tells us we can find this q and r. Now how can we calculate these? Well, actually using the floor function. So the quotient will just be m divided by n, the floor of that. So think of how this works. Think of just positive numbers right now. But when I do m divided by n, I'm going to get some whole part and then some decimal part. What the floor does for positive numbers is just cuts off the decimal. And so we're left with just the whole part, which is exactly what the quotient is. And then how do I get a hold of the thing that I chopped off? Well, I'll take the whole group and I'll subtract off the n groups, or the floor of m over n groups of n off of that and see how many are left over. And that'll be the remainder. And so with this, we can define the mod and div functions. So mod tells me the remainder, and div tells me the quotient. It just spits those things out given m and n. So we say m mod n. Notice that this is a commutative operation. Sorry, this is a non-commutative operation. I can't switch m and n here. So we have a direction to this. So m mod n equals the remainder, and m div n is that quotient. So that's what these things spit out. Let's take a look at an example just to see how this works. So if m, let's say m is 71 and n is 3, then we can calculate 71 div 3. This is spitting out the quotient. And so how do I calculate this? Well, I do 71 divided by 3. In this case, I get 23.666 repeating. So this is being able to just use pre-existing things. 23.666 repeating. And then the floor, so this, remember, is the floor of 71 over 3. And so this would spit out 23. And then 71 mod 3 is what's left over when there are the 23 groups of 3. So that is what's 71 minus the 23 groups of 3, 23 times 3, and that would be 2. And so what this means is we can write 71 equals the 23 groups of 3 with a remainder of 2. So that's how we can calculate mod and div. And this works as well for negative values of m. Remember, we restrict n to be positive. But m can be negative, so we could do something like negative 24 as m, and how about n equals 5? All right, in this case, negative 24 div 5. That's the floor of negative 24 over 5. So I'll take negative 24, divide that by 5 on my TI-34-2 calculator here. That's negative 4.8, so the floor of that I round down to negative 5. So this is negative 5. And then what's my remainder? Well, now that I know div, I can calculate that. Negative 24 mod 5 then would be, sorry, let's calculate it. Negative 24, that's the total, minus the negative 5 groups of 5. And that's 1. And so that means that 24, when broken into groups of 5, is a quotient of negative 5 groups of 5, with a remainder of 1. Sorry, negative 24. And so that's what negative 24 mod 5 is. All right, so how can we use this? Well, we'll actually be able to use this to prove some stuff. So let's check that out. So why is this helpful? And mod in particular is going to turn out to be very helpful. So recall in the division algorithm and therefore the outputs of div and mod that the remainder is always between 0 and n, exclusive on the n. So what this means is that for a particular n, so thinking a fixed n, there are only finitely many possibilities for m mod n, right? R can only be between 0 and n. And that'll be true for any integer I give you. It'll split them into these categories based on what is m mod n. And so what that means is that actually for each n, we receive a partition of the integer. So what do I mean by this? So for example, if n is 2, then if I look at any integer mod 2, it can either be 0, in which case it's even, it's divisible by 2, or 1, in which case it's odd, it's 1 more than 2. So this is sort of the partitioning of the integers into the evens and the odds is a specific kind of the partition I'm talking about. But we can do this with any n. So what about with 3? Why not? There's 3 possibilities for any integer, right? Either it's divisible by 3, or it'll have a remainder of 1 when divided by 3, or it'll have a remainder of 2 when divided by 3. So I get to split it into these categories. And what that means is that this is going to be really useful for proofs by cases, that if we know what the right m and what the right n should be, we can split this into cases. Right. So, for example, how is this helpful for us? Well, there's this theorem that we'll look at. Let n be an integer, then 3 divides n squared if and only if 3 divides n. This is pretty cool, a neat little result. And so how can we prove something like this? Well, notice one direction is pretty easy. If 3 divides n, it'll be pretty easy to show that 3 divides n squared. Why is that? Well, if 3 divides n, then we can write n equals 3 times some quotient, right? Q groups of 3 with 0 remainder. And then we know that n squared will be 3 squared times q squared, or 9 times q squared, or 3 times 3q squared. And so then we have n squared written as how many groups of 3? 3q squared of them, and there's still 0 remainder. And so that shows us that if 3 divides n, then 3 divides n squared. But how do I go the other way, starting with the assumption that 3 divides n squared? I could write n squared equals 3 times some quotient, but then to get to n, right, I'd have to take like a square root, and then things aren't even integers anymore. And so going this direction is a little bit harder. 3 divides n squared implies 3 divides n, and so we'll actually do it by contrapositive. And so the first part will be to assume that 3 does not divide n. Excuse me. If 3 does not divide n, what does this mean? Well, remember, 3 or any number mod 3, so any number when divided by 3 either has 0, in this case 3 divides, I'll say n here, 3 divides n, or it has a remainder of 1, or it has a remainder of 2. So if it doesn't divide n, it must have a remainder of 1 or a remainder of 2. That gives us two cases. Either either n equals 3q plus 1, or n equals 3q plus 2. And now we have something tangible to work with. Now we have like n, and we can look at n squared and see if that's divisible by 3 or not. Since we're doing a contrapositive, we'll be looking for the statement 3 does not divide n squared. So we'll hope to see some remainder when we square this. All right, let's take a look at the proof. So in the last slide, I talked through the backwards direction of this. So I've kind of already done, I'll write in the proof, the backwards direction done. We kind of already talked through that. If you want to see the whole proof in one thing, feel free to take a look at your book. And then the forward direction, we will go by contrapositive. And so we'll assume 3 does not divide n, then either n mod 3 equals 1, or n mod 3 equals 2, right? The idea here is that we've ruled out the case that n mod 3 is equal to 0 because we know 3 does not divide n. And that's what it means to divide n, is for the remainder to be 0. So we're just left with these two cases. So case 1 is when n mod 3 equals 1. And that means that we can write n as 3 times some quotient plus a remainder of 1. So that's my case 1. And then case 2, my n will be 3 times some quotient plus 2. So it splits all the possibilities into these two cases, and now we can look at n squared. So n squared then would be 3q plus 1 squared, in which case I get 9q squared plus 6q plus 1. And I want to figure out what that is mod 3. So notice we have n squared equals, I can pull a 3 out of a lot of this, 3q squared plus 2q, but I'll have a remainder of 1. So n squared mod 3 is 1. Hence, what do I want to show? I'm doing the contrapositive, so I assumed 3 does not divide n, and I want to show that 3 does not divide n squared. And that's what I have. N squared mod 3 is 1, which is not 0. Hence, 3 does not divide n squared. All right, let's see what happens in the other case. Again, we'll square n. So n squared is 3q plus 2 squared, 9q squared plus 612q plus 4. how can I pull 3's out of this? Well, I'm going to split up that last one. 9q squared plus 12q plus 3 plus 1. And then I'll pull a 3 out of that whole thing. And so I have n squared equals 3 times 3q squared plus 4q plus 1 with a remainder of 1 again. And so n squared mod 3 is equal to 1 in this case. Hence, again, 3 does not divide n squared. Notice we actually could have shown something stronger than what we proved here, because in either case, it turned out that n squared mod 3 was 1. So we could have stated this as 3 divides, or how do I want to say that? If 3 divides n squared, then either n squared mod 3 is 1 or n squared mod 3 is 2. So we could actually get a little bit stronger than what we just proved, but that's an example of how we can split. We generate cases by using mod because it partitions our integers. We'll get more into this idea of a partition in the next section, where we'll talk about congruence, and that's just the idea that two things are in the same part of the partition.